Hey everyone, what up though? So my name's Rob, and this is a course on an introduction to statistics for the psychological sciences. And this is the fourth and final part of a four-part lecture series. In the first two parts, we looked at frequency distributions, different types of frequency distributions. And then in the last portion of this lecture, we looked at measures of central tendency, which describe or approximate the midpoint of a distribution. And in this lecture, we're going to talk about measures of variability or spread about that center point to get a much clearer picture on the shape of the distribution we're dealing with. So I will just dive right in. So just to kind of recap, we talked about the mean as typically being the best guess of how a person would score. Typically in a normal distribution, the mean has the highest frequency of values, but an average is just an attempt to summarize a set of data with that best guess estimate. But what we need to describe the distribution more thoroughly is a measure of spread of the data around that mean. So, and this can be done either with population data or with sample data. So here we have an example of two different distributions. One way, and the most simple way, to assess variability in the distributions is the range. So the range is basically just the highest value in the distribution minus the lowest value in the distribution. So here we can look and see, for distribution A, the highest was about 70, the lowest is about 34. You subtract them from each other, you get a range of 36. And as is visually clear here, you look at range B or distribution B, and you get a much higher range, but still same procedure, right? So range is a way to describe the spread, but it has several different shortcomings, right? So in the same way that the mean is highly susceptible to outliers and highly influenced by outliers, so is the range, right? So if you look below here and you see these two red distributions, the one on the left and the one on the right are practically the same. However, a measure of range for these two distributions would be entirely different. It doesn't take every data point into account whenever the range is just highest minus lowest, right? And so the shape or how the data is inside of those data points is not, the range isn't sensitive to that. So in other words, it doesn't consider the entire distribution. And as a consequence, the range, while commonly used, does not provide a clear picture on the full shape of the distribution. More robust measures of variability are the standard deviation and the variance. So we want a measure that is going to take into account the deviation or spread in the data and reflect the true variability of the underlying distribution. But if you remember, one of the problems with the mean is that the mean was that balance point, and a property, what it means that it's a balance point is that the deviations away from the mean below the mean and the deviations away from the mean above the mean cancel out to zero when you add them up. So it doesn't matter what distribution that you have, what shape it is, anything. The mean, the property of the mean is that it balances out the deviations above and below to 0. So when we compute standard deviation, it may seem on the surface like we're using some kind of excessively complicated formula. But I want to walk you through how, why we're doing each step in computing the standard deviation. And it ties back to this feature of the mean as that balance point. So now we can compute variance and standard deviation measures using population data, but that's not very common. Most of the time, what we're going to be doing is sampling a group of participants from a larger population that they represent, and then when we compute our measures of dispersion, we're using them to estimate what the dispersion of the population is, right? So we're not so much interested in the standard deviation of the sample. We need to make some corrections to our sample standard deviation so that it is an estimate of the population standard deviation. And so for this reason, the formulas for computing variance and for computing variance and standard deviation are slightly different, and we'll go into that. But so what is a standard deviation? Well, basically, it's simply the average, a measure of the average distance between a score and its mean. And we can compute standard deviation by going through 4 steps. So the first step is we compute all of the deviations of each score from the mean. Next, we square each deviation. And the reason for this is because, as I said before, if we didn't, all of those deviations would add up to 0 every time, right? And so we square it so it doesn't add up to 0. Then we compute the mean of the squared deviations. So this value, the mean of the squared deviations away from the mean, is known as the variance. And so the variance is in units of squared deviation, right? But most of the time, we're not too interested in units of squared deviation. We want it back in normal raw units of deviation. And so we're going to take the square root of the variance to obtain that standard deviation, to convert it back. Now, when we're doing this for a population, we compute the average of the squared deviations as normal. But whenever we are using sample data to estimate the deviation of a population distribution, then we need to kind of correct for some overestimation. And the way we do that, underestimation. And the way we do that is we divide instead of dividing by the number of cases, we divide by n-1. Now, let me try to explain why we do this. So when we're estimating a population mean, for example, from a sample, you notice that there was no difference in the formula for a sample and a population. But this is because the mean is an unbiased estimate of the population mean. Again, the sample mean is an unbiased estimate of the population mean. However, the standard deviation of computed on sample data underestimates the population standard deviation. And so we have to provide a slight correction, right? And we do that by just saying n minus 1. And what you would, if you think about it, what this does is it makes it so that, say we had 10 people, right? So we would have n minus 1, 9. But as the number of people in our sample increases, right? If we have 100, the magnitude of that correction goes down. So our estimate of the population standard deviation from the sample becomes stronger as our sample size increases. And so this is a way, and you'll see this throughout this course, that we kind of correct for or adjust our estimates so that they more appropriately reflect what we would expect in a population. So let's just go through each of these steps. So the first step is we are going to compute the deviation from the mean for each score. So we did this last class when we were talking about properties of the mean. And so essentially, we have a deviation here of 2, a deviation here of minus 4, a deviation here of 4, a deviation of minus 1, and a deviation of minus 1. So essentially, we go through and just log these down, right? We put our deviations down. So we have the value, the mean, and then the deviation from that mean. And the next thing we do in step 2 is we square those deviations, right? So it's simply taking the deviation, multiplying it by itself. Okay, and then in step 3, we compute what's known as the sum of squares. What sum of squares is? It's the sum of the squared deviations away from the mean. We are going to be using sum of squares in almost every lecture after this one. So this is a very important concept, right? So essentially we take all of the squared deviations away from the mean, we add them up. Now keep in mind, right, these squares, none of them can be negative. If there are negative numbers, right, something's gone wrong. But we do this for our population data. And then if we're dealing with a population, we just divide it by n. It's just the average of those squared deviations. If we are estimating population data from a sample, we make our correction by dividing by n minus 1 instead of n. And so you can see here that because sample data tends to underestimate the population mean, we basically make this correction, right, which inflates the sample mean. Okay. Next thing we do is we take the square root of the answer to find the standard deviation. Oh, my mistake. Let me go back here. Once we find the average sum of the squared deviations, that value is known as the variance. The variance is simply the average of the squared deviations away from the mean. Variance is a great measure, but most of the time we aren't interested, and it's more challenging to interpret what that means. So we want to convert it back into raw units that our original measure was in. And because we squared it earlier, the way we do that is we just take the square root, right? And so that's what we're doing here in step 4. What we have here is, we just square those average deviations, and that is the standard deviation. In other words, the standard deviation represents the square root of the average of the squared deviations from the mean. That's for a population. It's the same for a sample, except it's not entirely an average because we have that correction of n minus 1 instead of using n. Okay, well, all right, so why square it? I mean, there's other things that you could do. You could, like, take the absolute value. Wouldn't the absolute value do the same thing? Well, that is a very intuitive question if you had that question. So you could. However, there are other properties of standard deviation that involve squaring that make other computations we're going to do down the road much easier. The other thing is there is a difference in that when we square the values, the more extreme values are weighted more heavily in our estimate of the standard deviation. So it is slightly different. Okay. So we've already really kind of talked on variance. It's the intermediate calculation before we square root it. It's the what you compute in step 4. Alternatively, you could take standard deviation and just square it, and you get the variance. So, plainly, squared standard deviation is variance, and the square root of the variance is standard deviation. Variance is just another measure of variability or dispersion. So, again, here, I mean, the same with standard deviation, we have the population variance, which is just divided by n. It's the average of the sum of squares. But the sample variance is divided by n minus 1, this correction for our estimate. And this is probably a good time to just remind you, anytime you see a Greek letter, we're referring to a population parameter. Whenever a formula is in an Arabic letter, like here s squared, we're dealing with a sample value. This is an important distinction. The formulas may be the same or similar, but conceptually, that's where it really matters. You need to understand that we're not computing variance and standard deviations of our sample. We are adjusting what it would be for our sample to make an appropriate estimate for the population that sample represents. Now, we just walked through kind of like the conceptual step-by-step process of how to compute variance and standard deviation. But whenever you're confronted with problems that have, considerably more data in them, that would be very tedious to do. So here is a more efficient way to compute sum of squares by hand. This is the computational formula. It's going to produce the exact same answer as kind of the definitional formula we went through, but it's simpler to calculate. So keep in mind, it's going to be n minus 1 if it's a sample. I also want to bring your attention to the importance of order of operations here. Inevitably, people will struggle with this. They do every semester. So let's look at what is expected in that equation. The first part, the sum of x squared, right? There's no parentheses there, right? You're going to square, right? It's the E in PEMDAS. You're going to square all of the values and then add them up. In the second part, however, since it's in parentheses, you're going to add up all of the raw values and square the total before you divide by n. So make sure that it's a very simple mistake to make, but it will lead to dramatically wild miscalculations if you're not mindful of that distinction. So please be careful. Okay, so here is, the full shortcut, right? So we have the sum of x squared minus the sum of x, and then square it, divided by n. So that's going to give you the sum of squares value. Then you can just drop it in to your equation with standard deviation, right? So the standard deviation of the population is divided by n, and the standard deviation of the sample is divided by n minus 1. This does not change. The sum of squares is always divided by n, just to be clear. Sum of squares is always divided by n. It's when you plug it into the formula for standard deviation or sample standard deviation, that's when we're gonna make the adjustment for estimation. Okay. So if you're given numerical values for the mean and the standard deviation, you should be able to visualize what that distribution is going to look like. Now, there's some pretty slick properties that normal distributions have, and I'm going to hold off on much of it until next class, when that's going to be the focal topic. Or the normal distribution is one major aspect. But as a general rule, with a normal distribution, 68% of all scores will fall within one standard deviation of the mean, and 95% will fall within a distance of 2 standard deviations from the mean. So here's what this looks like. This is an interesting property of the normal distribution. And because of this property, we are able to approximate, we can kind of leverage this property of the normal distribution to make fairly accurate predictions about what proportion of people will fall above or below a certain score, and various things like this. And we will go into that in the next lecture. I know this one's been long. This is another unit that had a lot of material. But moving forward, I'm hopeful that you have soaked in all of this introductory conceptual stuff. And as we move forward, I'm hoping that it will get much more interesting as we begin to actually start to shape how we're able to make predictions about entire populations of people from a small little subset sample of people that we have access to. Thank you for listening. And if you haven't already, don't forget to install SPSS. It will be absolutely necessary moving forward. Have a good evening.